triangle, right? Here's how it looks. We know that each term in the Pascal's triangle is the sum of the other two terms above it. And do you remember what the Pascal's triangle gives us in the expansion? You're right, it gives us the binomial coefficients. What was the next concept we had studied? Yes, it's permutations and combinations. We will be requiring only combinations here. We all remember the formula of combinations, right? Yes, it was NCR equals n factorial over n minus r factorial times r factorial. What does NCR mean here? NCR represents n items taken r at a time, where the order in which the items are chosen does not matter. Now, let me ask you one question. Can you tell me the value of 2C0? Yes, we can use this formula. We get it as 2 factorial over 0 factorial multiplied by 2 factorial. We know that 0 factorial is 1. So we get this value as 1. Now by using the same formula, can you tell me the value of 2C1? Yes, it's 2. Now try getting the value of 2C2 as well. Do you get it as 1? Yes, that's right. We got the three values as 1, 2, 1. Now take a look at the Pascal's triangle. Did you notice something? Yes, we have these same values in the second row. Do you think there is some relation here between combinations and the Pascal's triangle? Let's find out. Calculate the values of 3C0, 3C1, 3C2 and 3C3 by yourself. Did you get it as 1331? You're absolutely right. Have we seen these terms previously anywhere? Oh yes, these terms form the third row of the Pascal's triangle. What can you conclude from this? Can you derive any relation between the Pascal's triangle and combinations? Give it a try. Each number in the Pascal's triangle is given by a combination NCR, where n is the row number and r will be the number in the range 0 to n. Let's try and understand this better. We saw how it works for the third row. N here is 3 and r ranges from 0 to 3. What if we want to find the terms in the sixth row of the Pascal's triangle? How do we do that? We know the relation between combinations and each term, right? Let's use that to find out each term. We have to find the numbers in the sixth row. So here, n will be equal to 6 and r will take values from 0 to 6. By using the formula of combinations, we find the values of 6C0, 6C1, 6C2 and so on up to 6C6. Try finding out each of these values using the formula we saw earlier. We get these values as 1, 6, 15, 20, 15, 6 and 1. And yes, these are the terms in the sixth row of the Pascal's triangle. But why do we use combinations when we can draw the Pascal's triangle and get the values? Think about it. Now let's assume we have to find the terms in the eighth row. Will we draw the Pascal's triangle up to the eighth row? Or will we simply use combinations and get each number? Yes, we will use combinations. Using combinations will make our work much simpler. Say we have to expand the binomial a plus b raised to any positive integer. We know that to get the binomial coefficients, we can use the formula of combinations. But how do we get the other terms consisting of a and b? What do I mean when I say other terms? Take these two identities for instance. Now using the combination formula, we will get 121 and 1331. But what about these parts? Let's see. Look at the formula of a plus b the whole cubed. Observe the first term. Can you tell me the power of a here? Yes, it's 3. Now tell me the power of a here. It's 2. And what's the power here? The power is 1. Now, what's the power of a in the last term? The last term does not have a at all. This means that the power of a here is 0. So it's 3210. Now let's look at b. Can you tell me the power of b in each term? Yes, they're 0, 1, 2 and 3. Didn't you notice any pattern in the powers of a and b? Yes, we observe that the power of a decreases and the power of b increases in each term. For a, the powers are 3, 2, 1, 0, and for b, the powers are 0, 1, 2, 3. Let's try and generalize a formula for this. Consider a plus b raised to n, where n is any positive integer. First, let's write the binomial coefficients given by the formula of combinations. So we have NC0, NC1, NC2 and so on up to NCn. We've left gaps here because the terms are not complete yet. We can complete the terms now. We know that the power of a decreases from left to right. So let's write a with each term having decreasing powers. We have a to the power n here. How do we write the power of a in the second term now? Yes, as the power decreases, we can write it as a to the power n minus 1 and then a to the power n minus 2 and so on. The last term will not have a as it's a raised to 0, which is nothing but 1. We're not done yet. What about b? We write b with each term having increasing powers. That is from 0 to n. So can you complete the formula now? Here's how it will look. The first term will have b to the power 0, which is nothing but 1. Then we have b to the power 1, which is b, then b squared and so on. The last term will have b to the power n. There you go. We have the general formula which will help us expand the binomial of any power very easily.